All right. So as I was saying, I hope you guys had a great break. Hope you enjoyed a little time off from school and a little time off from thinking about physics. But hopefully you're also ready to jump back in and get going on second semester. Um, Second semester is going to feel faster paced in terms of the content we cover. The first semester, we really lay the foundation, really getting to know everything we can about kinematics, everything we can about forces. And then this semester, it's going to be okay, well, now that we know that as your foundation, how can we use all of that to figure out how much work is done, how much power is required, how much energy is consumed? And then we'll talk about, well, how does that relate when something's spinning? How does it relate when something's going in a circle? And we'll just keep kind of expanding and expanding and expanding. There isn't going to be real long units broken into multiple parts like we had last semester. It's going to be 2 or 3 weeks, units done, 2 or 3 weeks, units done, and just kind of clips through much quicker. So it'll feel a little bit different that way. And so it's real important that you don't ever let yourself fall behind, because there's not going to be those long stretches between tests anymore. It's going to come much more rapid fire. So we'll probably have 2 tests before ski week break, and then we'll have 2 or 3 tests before spring break in that middle section. And then right after spring break, we'll have maybe one more test and then a couple weeks to review. So it'll just fly by with all the breaks and as fast as we go through the unit. So just be prepared for that. And because we have so many students out, this is actually the best attendance I've had all day. We only have one student missing, and he's here online with us. So good to see you, Charlie, online. Glad you could make it. But I know there's going to be more students out with cold, flu, COVID, other stuff. I mean, it's going to be kind of, I think, that way for the next few weeks, probably. So my plan is to every day, I have at least one student in every class who's approved to follow on Zoom. So every day I just plan to have Zoom running for the next week or two at least. And I'll be recording at least one of the sessions from one of my 4 periods. And so today I'm going to record this one because I have lunch break after this, so then I can edit it and upload it. And if you ever miss class and you need to see the video, you'll be able to find that if you go to the bulletin board page, and then there's in the links section, that's where the Zoom link is, so if you ever need to join by Zoom. And then there's also a link for my teacher YouTube channel. And so if you just click on that, you can go and you'll see a CP Physics playlist, AP Physics 1, which is obviously yours, and you'll see some other playlists. But go to the AP Physics 1 playlist, and I'm just titling them by the date. And so it may or may not be your class period, but you can follow along and see what you missed by watching the video. And then in the announcements on bulletin board, I'm also just going to put a quick brief, okay, this is the agenda that we did for the day. And so if you miss, you can look at the announcement, see what the agenda was, then you can go to the Zoom link if you're going to attend virtually, and then you can go to the YouTube channel and watch the video if you can't attend virtually or in person. Right, so that way you'll be able to keep up on the assignments, know what you're missing, not miss any notes, and then all the handouts and things we do. So for instance, this handout, and Charlie, you can find it, it's in the, let's see, I think it's, let me double check the exact number because all my numbers are different in different classes, but that's that's this one, 2B. So if you look in 2B, there was a couple of quick topics that I wanted to make sure we covered. So the notes we're going to go over today are right here, electric force notes. Tomorrow is going to be gravitation notes. And then we're not going to do either of these separate worksheets, but we are doing this worksheet 3. So that's the one that you guys picked up from the back of the room today. So Charlie, you should be able to find it there on Access in Unit 2B. And then anyone watching the video, hopefully it'll, even if you're not in section 2, it's going to be in the same unit for you if you're in AP 1. So actually, let me share that because I don't think you could probably see that. So it's in 2B right here. So that way it'll show up on the video as well. All right, so there's the notes for tomorrow. There's the notes for today, electric force, and then worksheet 3 right here. All right. So I switched it to share screen instead of individual files. So can you see the notes again now, Charlie? The agenda?
Yeah.
Okay, good. Could you see Access there for just a minute?
Yes.
Okay, good. I'm glad it's working. All right, so that's how it's going to work. It's going to be, like I said, probably a little bit different. Fortunately, on my side of things, I will be more available. So if you need help from me, I don't think I'm going to have to be running out to help the grandkids or anything like that. Right during exam week, my daughter and her kids moved to Texas to be with her husband, who's in the Army there, stationed in San Antonio. They made it safely. She had her baby yesterday. And so, yeah, everything's kind of on even keel, and it's just me and my wife at our house. So I won't have to be running out for emergencies or things. So I'll be available to help after school more frequently than I was there towards the end of first semester. And also always available during lunch if you want to come in. One thing you could do in those times is come in and see your semester one exam. And we're not going to take any class time to go over it because the time is so short between now and the test with all these little choppy, 6 weeks and a break and then 5 weeks and a break. And we just have to keep going on pace. We're not going to steal any class time to go over that semester one exam, but I'm going to keep them up here in the classroom for a couple of weeks in case you want to come in and look it over or talk it over with me. You're welcome to do that. The grades were automatically curved. You don't have to do corrections on the exam to get the curve. And it was actually kind of a double curve. One of the test questions that table didn't print properly. And so I just dropped that from the test for everybody. And then there was another question that I just saw a lot of people struggling with, and when I read the wording, I could see why it might be a bit confusing, so I dropped that as well. So I dropped 2 of them, and then after dropping it, then I applied the regular AP curve. So you got kind of a double curve in a sense. Did you have a question, Lexi?
After lunch today, could we look at the exam?
Yeah, anytime. You're welcome to come in today, or any day in the next couple weeks. So the other thing that I want to mention, though, as I was reading and grading your free response questions, I noticed there seems to be some confusion that's fairly consistent about exponential versus quadratic relationships, because there were probably 6 or 8 students that used the term exponential to describe what really should be quadratic. So I want to review that quickly to make sure that everybody's clear on the difference. And then we're going to talk about electric force. Now, this is one I'm only going to talk about it today, and then we're going to move on because I don't think it's going to be on the test this year based on how they changed the formula sheet. But it has been on the test every year up until now, even after they changed the curriculum. So just since it's no longer on the formula sheet, I assume that means they're dropping it. But just in case, I want to introduce it to you. We'll just spend a short period today going over it. The other reason I want to do it is because it is one of the 4 fundamental forces of nature. And so I think understanding it is pretty important, even if it doesn't show up on the exam in May. The way I will test you over it for our test on this part of the course will just be a multiple choice question. So it'll just be one question just to see if you got it. But I want to introduce it today. And it's also a good math practice because it requires you to do some things both with your calculator and just with your math knowledge that we haven't done much of yet this first semester. And it's going to apply very directly to tomorrow's lesson on gravitation and to some other things we're going to learn this semester. So even though it's unlikely to be on the May exam, there's some other good benefits for covering it. So that's what we're going to do today. And then we're going to do just one question off that worksheet for this part of the unit. We're going to do other questions from the worksheet in tomorrow's lesson. Tomorrow's lesson is going to be on gravitation, which will for sure be on the May exam by College Board, and also definitely on your exam for me. Now, we will be just taking today and tomorrow to wrap up these last little loose ends from our unit on forces. And then starting next week, we're going to just jump right into the next unit on College Board, okay, and in our class as well. So first, let's talk about exponential versus quadratic. So there were a number of students who saw data on the exam and the free response question and saw that it was nonlinear and said that the relationship looked exponential. And I didn't count off because it's true that it might look exponential, but if you look over the equations we have from College Board, all the ones that we would possibly be tested, there are no exponential formulas for this course. And so you can sort of drop that exponential relationship from your vocabulary terminology as you're answering questions, because it will never be an exponential relationship for this course, all right? If you see that curve, it's just showing you part of a parabola. It's just showing you part of what's actually quadratic. because the only relationships we're learning are either linear or quadratic or inverse. There's not going to be any exponential. And just to give you the quick reminder of how they're different, obviously linear is just when x and y, neither one has an exponent on it. They're both first power. Quadratic is when either the y or the x is squared. So not both, but one or the other. And then exponential is when the x is the exponent, right? So the exponent's actually changing, and that's not something we cover in this course. There aren't any AP Physics 1 equations that have that relationship. In AP Physics 2, there are some, but in this course, there aren't. So you won't ever expect in this course to be asked to explain an exponential relationship. So just make sure you're aware of that difference. And if you're answering an FRQ for College Board, I expect they would probably not be as forgiving as I was, because I circled it, but I didn't take off any points, even though it should have been quadratic. It would be safer to say nonlinear than to use the term exponential, because I think they might deduct for that. Okay, so just want to make sure you're aware of that as we get closer and closer to that May exam. We do have a little bit of an advantage this year. For the first year in quite a while, the physics exams are in week 2. And so we have an extra week to prepare. It gives us a little bit more time to review. But that's a little bit down the road still, although I'm sure May will be here before we know it. So any questions about the difference there between exponential and quadratic? All right, so let's jump into electric force. There are 4 fundamental forces: gravity, electric or electromagnetic force, and then the strong and the weak forces, which are more towards the chemistry side of things. We talk a little bit about strong and weak force in AP Physics 2 when we talk about modern physics, but in this course, it's primarily gravity and electromagnetic or electric force that would apply to what we're learning. So again, I don't think that you're going to be asked to define this or even use the equation on the May exam, but because it's one of the fundamental forces, and because mathematically it's virtually identical to the gravitation equation, I think it's good practice for us to still learn about it just this one day. All right, could I get someone to read this slide? And Charlie, you're welcome to jump in and read as well if you'd like. Can I get someone to read this one for us? Hey, Lexi.
Newton's first law of inertia states that objects moving at a certain velocity will maintain that velocity unless acted on by an external force. Objects will only accelerate if acted on by an external force. If a free rod accelerates towards the stationary rod, there must be a force there. We call this the electric force. As with all forces, it is measured in Newton.
All right, so if there were some reason why this rod was accelerated towards the other one, either because there was an external force pushing it or because there was enough of an attraction to pull them together, that force pulling them together or repelling them apart could be the electric force. And it is in a lot of ways no different than the forces we learned about last semester. No different in the sense that the electric force still obeys all 3 Newton's laws. So when that force causes an acceleration, that object will experience that acceleration proportionally to the force applied and the mass of the object. All right, so you can still apply all of those Newton's laws. Newton's 3rd law will still apply. If there is electric force between 2 objects, then they will experience the same force just in opposite directions. Okay, so it gets a little bit different in the fact that we have to also consider whether they would be attracted together or repelled by the charges. And we'll get to that here in today's lesson. But everything about forces that we've learned so far, the units, Newton's laws, all of those things still apply. All right.
So with electric force, is this just like magnets?
Well, in the big fundamental forces, they call it electromagnetism because electricity and magnetism go hand in hand. So that's more of an AP Physics 2 topic, so I don't want to spend too much time on it now, but basically when you have a charged particle that's moving, it generates a magnetic field. So the magnetic fields and the magnetic force come from movement of charged particles, which generates electric force. So there's a relationship, but they're not quite the same. All right. Can I get someone else to read this one for us?
In the late 18th century, Joseph Priestley reasoned and John Robinson measured that the force between two objects followed the same principles as the gravitational force, and that the force between two charged objects depends on the inverse square of the distance between them.
All right, so this is just a relationship showing that that electric force is going to be proportional or depends on the inverse of the radius or the distance between them squared. And this is where the big one of the big connections between electric force and gravitational force exists. So discovering it now with electric force is going to carry on over into tomorrow's lesson. I guess for you guys it'll be Friday. And that lesson will be just, like I said, the same kind of relationship. And I know gravitational force is going to be on your May exam from College Board. So we're just getting a head start on it. So if you think about magnets, because Charlie mentioned that there's a big connection between magnets and electricity. If magnets get further apart, is the attraction stronger or weaker? Weaker. The farther apart they are, the weaker it gets. Okay. The same is true for the attraction or repulsion of charges electrically. So the farther apart they are, the weaker the attraction, or the weaker the repulsion. And it's not a linear change. It's a quadratic change. It's a squared change. We call this an inverse square relationship. And there's a lot of things in physics. There's only a couple that we learn in AP 1, but then there's even more that we learn in AP 2. So it's a very common trend we see in nature, that this inverse square relationship exists for a lot of things. All right, can we get someone to read this one for us? Okay, Chris.
Charles Collin published a paper in 1785 based on detailed experiments that definitively proved Priestley and Robinson's work, that the force was also proportional to the size of the charges. He used a torsion balance, which was based on the same principle as Henry Cavendish's experiments that measured the gravitational constant.
All right, so you can see I'm being a little sneaky. We're talking about electric force, but I keep talking about gravity at the same time. So I'm trying to lay that foundation for something I know you need to know that we'll dig into more tomorrow. And we'll talk more about Cavendish's experiment tomorrow, but the basic idea of how these two gentlemen determined the values was the same idea. They tried to look at something rotating and measure how much rotation occurred. So we'll dig into how exactly that looked tomorrow with gravity. All right, so we won't have anybody read this one, but I'll just highlight a few things here. This is the equation that used to be on the formula sheet, but is no longer there. So I would encourage you, just in case, go ahead and write this equation wherever you are keeping your equations that I give you in class that aren't given to you that you just might need to know. So I've encouraged you to possibly consider like putting it on this blank space here at the bottom of your formula sheet, or maybe you've set aside a certain page in your notes. This is one that, again, I don't expect it's going to be on the May exam, but it will be on your test that we take, just one question, just in case. And when we talk about gravity tomorrow, you're going to see that the equation is virtually identical. So it wouldn't be hard to remember because they do give you the gravitation equation on this sheet. So as you look at the equation, F sub E just stands for electric force. K is what we call Coulomb's constant. And this is, the whole equation is called Coulomb's law. And you can see in the first line there underneath the equation, you'll definitely want to write this down as well, that the K value is equal to this 9 times 10 to the 9th newtons times meters squared over Coulomb squared. So definitely want this number recorded. That is the value of K, constant section, and it is still there. And that's why I'm a little bit wondering whether they might still ask you this. I can't think of any other reason why they would include this except for this one equation, but they haven't given you the equation, but they have given you the constant. That's why I'm a little bit unsure whether you're going to be tested over by College Board. So I feel like it's safer to spend this one day to at least teach it to you. So the K value is here. Unfortunately, the equation is not on the other side where it used to be. These letters Q, Q1 and Q2 stand for charge. So the charge of object 1 and the charge of object 2. and we measure charge with units called coulombs. So this equation is called Coulomb's law. The constant letter K is called Coulomb's constant. And the unit for a charge is a coulomb. So that's what this C squared is. That capital C stands for coulombs. That's the charge value, the unit for charge. And you notice there's absolute values on it. We don't really care about the sign in terms of determining the magnitude. We only care about the sign to decide whether they would be repelling each other or attracting each other. And we can see that without plugging it into the equation. All right, so we use the absolute values there on those charges. And then the R value underneath that is squared, you'll notice down here they listed it as R12. It looks like R12, but that really is R12, the distance from charge 1 to charge 2. And that pattern will also show up in gravity tomorrow, or Friday, and then it'll also show up in some other things we learned this semester in other equations. So when you see a subscript that looks like a 12, for instance, or a 13, most likely they're saying it's between those two things. So this would be the radial distance from object 1 to object 2. So it looks like a 12, but it's really just referring to the two objects that have charge in this situation. And then again, just I mentioned it a couple times, but this equation is mathematically similar to the universal law of gravitation, which is on the formula sheet. It's right here. So I know you're still expected to know that, and we'll dig into that one tomorrow. All right, any questions about this equation, what the variables mean, what the units mean, anything at all that you want to ask before we move on here? All right, how many of you have had chemistry already? Okay, or you're in chemistry now? Okay, all right, good. So some of what we talk about in these next few slides will be clearer, I think, if you've had chemistry. But even if you just had middle school science, you probably know enough chemistry to follow. If you have questions, though, slow us down and ask. If you haven't had chemistry, it's not quite sinking in, let me know. All right, so can I get someone to read this one for us? Okay, Lexi.
Coulomb's law is used to calculate the magnitude of the force. Each object exerts the same force on the other except in the opposite directions. Newton's third law applies to all forces, not only mechanical ones. Since electric force, like all force, is a vector, you need to specify the direction of the force whose magnitude was determined by Coulomb's law. This is done by looking at the signs of both charges, like charges repel and opposite charges attract.
All right, so that last little phrase in parentheses is actually the most important part of what you need to know from this chemistry connection, that like charges repel and opposites attract. And then in terms of the Newton's laws, like we said, all the Newton's laws apply. And so that Newton's third law applies here just like it applies on any other force. All right, continue on. Get someone to read this one for us. Just kind of summing up the equation. Okay, Jordan?
Both forces are expressed using a similar mathematical formula where the magnitude of the force decreases as 1 over r squared. Electric force can be attractive or repulsive. Like charges repel, opposite charges attract. Gravitational force is always attractive. The electric force is on the order of 10 to the 36 times stronger than the gravitational forces.
All right. So while gravity and electromagnetic forces are two of the fundamental forces, electric force or electromagnetic force is billions of times larger. It's many orders of magnitude larger than gravity. And so we think of gravity feeling so powerful, but it's only because we're so small compared to the Earth. And electromagnetic forces are far more powerful, far more impacting to everything around us. Not as obviously, because most of it happens at the atomic level where you can't really see it happening, but it is happening all the time. All right, and then someone read this one for us. Someone help out Lexi here, she didn't have to read it all. Yeah, thanks, Parker.
Electrical force relationships to contact forces. Dynamics cover the contact forces, such as normal tension and friction. Newton's third law applied to them, as it also applies to the electrical force. Is there some deeper connection between electrical and the contact force? And what are cars, baseball, water, and people made of?
So what are all those things made of?
Matter.
Matter, and what's matter made of?
Atoms.
Atoms, and what are atoms made of?
Protons, neutrons, and electrons.
Protons, neutrons, and electrons. And what do we know about protons, neutrons, and electrons? We won't go down to the quarks level, but that is true, it keeps going. But if we stop there at that level, protons, neutrons, electrons, what do you know about those particles?
Have electricity.
Two of them have charge, right? Protons are
Positive.
positively charged, electrons are,
Negative.
and for those that have had chemistry, or maybe just you know anyway, what's true about the value of the charge for a proton and the value of a charge for an electron?
They're equal.
Equal in value, just opposite in charge, right? Now, if you look on the formula sheet, if you have your copy with you, it has on here the mass of a proton, mass of a neutron, mass of an electron, and over here it has electron charge magnitude. That is the value in coulombs for the charge of an electron. That is also the value in coulombs for the charge of a proton. It doesn't say that, but it is, okay? Protons and electrons have the same magnitude of charge. And you can see it's a very small number, times 10 to the negative 19th for a single electron or a single proton. All right, so since all particles are made of charged subatomic particles, like all matter is made of those charged subatomic particles, then maybe that's the connection, and they're going to try to flesh that out for us here on these last couple slides. All right, could I get someone to read this one for us? I'll be brave.
I can do it.
All right, thanks, Charlie.
Electric force relationship to contact forces. Large macro objects are made of atoms. Atoms are composed of a positive nucleus surrounded by a cloud of negative electrons. The predominant force acting between atoms is the electric force. At the macro level, the predominant force is still the electric force. Since there are so many atoms involved at this level, it is easier to describe these interactions in terms of non-fundamental forces, such as the normal force, tension force, and friction.
All right, so actually all those things we've been talking about are caused by the interactions of the protons and electrons at the atomic level. But we can't see that happening because it's at such a small scale. So rather than talking about it at that small scale down to the electric force, we look at it at a more macro level and talk about, well, normal force is when those surfaces are in contact, and friction is what impedes motion when those surfaces are in contact. And tension is the attraction basically between the atoms and molecules in the rope or the cable or the twine or the wire that's trying to be stretched, right? And so it really does come down to, for all of those things we've learned, it comes down to technically the source being electric force. But it's just hard to see that, it's hard to measure that. It's much easier to see and measure those macro level normal forces, tension forces, and friction forces. All right, so the normal tension and friction forces are called contact forces. They involve touching. Now, I put touching in quotations because technically there's always going to be some amount of space. Again, those that have had chemistry know that atoms are mostly space, right? The nucleus is really, really tiny, and electrons are moving in sort of a cloud of arrangement, energy levels around that nucleus, and there's a bunch of space in there. And so, since everything's made of atoms and atoms are mostly space, the objects here technically aren't really touching. We feel pressure because of the repulsions and attractions, but technically they're not truly touching in the way we think they are. But all of those contact forces are generated because of the electric force. All right, so from today's lesson, and I know we haven't covered gravitational yet, but I sort of secretly started covering it today. Not so secretly, but what are some things that are same or different? Compare and contrast the gravitational force, which you've only hinted at, and the electric force, which we've now covered. Lexi, what you got?
The electric force is much stronger.
Electric force is much, much stronger than the gravitational force. What else do we have? Comparisons and contrasts. Yeah, Dominic.
Electric force works on like a much smaller scale.
We're talking at the atomic and subatomic levels. Good. Yeah, Chris?
They have similar equations with just different variables.
Excellent. Yeah, their format of the equations, if you had a chance to look at the gravity one on the formula sheet, it looks identical in form, just different letters. And so, yeah, they are mathematically identical, just different variables. Excellent. Yeah, Aiden.
Both decrease in a quadratic inverse relationship. They both decrease like more and more as you go farther away from the two objects.
Yeah, they have that same inverse square, inverse quadratic relationship where the farther they are apart, the weaker the value of that force. Anything else? You guys have hit all the main spots, but is there anything else you want to add? All right, they are both fundamental forces. We could also mention that, but that's not the key thing that I'm trying to highlight. So here are the things that I think you came up with all of them. The electric force, oh, I don't think anybody said this actually, but so let's make sure we remember this. The electric force can be either attractive or repulsive. So they can push away or pull together. Gravity is always attractive. Gravity always only pulls things towards each other. But you guys did mention electric force is much stronger. You mentioned that their formulas are the same or similar, and you even talked about how they're similar and what ways are they similar and different. So those are some key things that you would want to know about how electric force and gravitational force are both similar in some ways, but different in others. All right. So let's try it. We've got a positive 20. Now that little symbol in front of the C looks like the coefficient of friction, right? It's the same Greek letter, but it's not a variable here, it's a unit. When it's a unit, what does that little mu symbol mean? Anybody know?
Nano.
Close. It's like that nano, milli, micro, yeah. So that is the symbol for micro. So it's positive 20 microcoulombs. What's the metric conversion for micro? It's actually on the formula sheet as well. 10 to the negative 6. So 20 times 10 to the negative 6 coulombs. All right, very small amount of charge. It's a small amount of charge, but it's a point charge located 20 centimeters away from a negative 40 microcoulomb point charge. What is the force on each due to the other? What do we know about the value of the force between number 1 to number 2 or number 2 to number 1? It has to be true about that magnitude. Equal, because of? Yeah, Newton's third law. They have to be equal, they're just opposite. Now, will these attract each other or repel each other? We've got a negative and a positive, they will attract. Opposites attract. All right, so if you look down here, before you even do the math, which ones do you know it has to be? Either B or D, because if we have a positive and a negative, they're going to attract. And if they attract, they're going to move towards each other. So it's got to be B or D. Now it's a matter of plugging the numbers in to see which one is correct. Now, if you look at the units for the K value, it is newtons times meters squared. So we got to change that centimeters. Okay. And then divided by coulombs squared. So we got to change these microcoulombs. All right. I'd actually like you to get your calculator out and try it, or borrow one of mine if you didn't bring yours or if it's dead. But I want you to try this because this often causes a lot of students problems. And if it causes you problems today in electric, it's going to cause you the same problems tomorrow with gravity.
one's 20, Q2 is 40.
Yeah.
And K is 9 zeros.
Pretty much, yeah.
So 20 times 40.
When you think you know whether it's B or D, raise your hand so I can kind of keep track of timing. Okay. Give you a little more time for those that are working. Can we see a show of hands again now? How many have been able to figure it out? A few more. All right, let me show you a couple things on the calculator that you may or may not be aware of, that if you're not getting the right answer, then this may help you figure out why. So those of you that have an answer, which one is it, B or D?
D.
D as in dog?
Yeah.
All right, yeah, that is the correct answer. It's not a matter of not understanding the equation, it's usually a matter of not getting it put into the calculator in a way that your calculator can interpret it correctly. So let me just talk you through that. So K is 9 times 10 to the 9, and you can type 9 times 10 and then raise it to the power 9. You can do that, that is fine, but then you need to use parentheses, and not around the 9 though. You need to use it both in front and behind. If you don't use the parentheses, you won't get the correct answer. Okay. Now, there's a shortcut to that though that allows you to avoid all those parentheses. So if you just do 9 and then use this EE button down here, it's right above the pi button, right beside the A button. And it just shows, it's 2 E's on the button, but it only shows 1 E on the screen. And so 9 times 10 to the 9 looks like this. You type 9, EE 9, and that means 9 times 10 to the 9th. And then you don't have to use any parentheses. So it doesn't look like 9 times 10 to the 9th, but that's what it means. Okay, so that's your, if you haven't learned how to use that function, that's your shortcut, and it saves a lot of time putting in parentheses, and you don't have to type as much. You have to type in the times 10 and the caret button, just 9 EE 9. And then we need to do the charges. So Q1 was 20. We don't need to worry about the plus or minus because it's absolute value. So 20 EE negative 6. And you have to use the negative sign that's here beside the enter button. It's between the enter and the decimal. You can't use the subtraction button. It has to be the negative 6. That's the micro part. Okay, the 20 microcoulombs. All right. And then times the second charge, which is 40. And then we have to do EE negative 6 because it's microcoulombs again. And then I usually put parentheses around the whole thing. And if you do it this way, when you hit the parentheses at the end, it automatically adds it at the beginning. So that's what your numerator would be. 9 times 10 to the 9th times 20 times 10 to the negative 6th times 40 times 10 to the negative 6th. Okay, that's how you can put that in. And then we need to divide that by the distance between them squared. And was it 20 centimeters?
Yeah.
So we need to do 0.2 because we need to change it to meters, and then we need to square it. All right, and so we should get 180. All right. So a few things, you either need to expand it out or use parentheses or use that EE button to avoid having the calculator give you a wrong answer. Any questions about that? All right, so my goal is to put a question much like this on your test. So right now, today and tomorrow, we're wrapping up a few loose ends from forces, Unit 2. Next week, we're jumping right into Unit 3. So I'm not going to have a separate test, obviously, on these tiny little loose ends. I'm just going to wrap it up into the Unit 3. And so when we take our Unit 3 test, I will put one electric force question like this, multiple choice kind of deal, and ask you to solve it. All right? Now, your assignment is to try number 7 from the worksheet, but I want to give you just a couple of hints.
Now?
Yeah, I mean, it's due next time. We've got, what, about 2 minutes left? So I'd like you, as your assignment, I'd like you to try just number 7. So you got a worksheet with 8 questions. Don't worry about any of them except for number 7. All right? And here's your hint. You're going to have to use just as much from first semester to solve this question as you did from today's lesson. All right? You'll have to use today's lesson, but you're going to have to remember how to think through the trig we did last semester so you can get an angle. You're going to have to think through how to draw a free body diagram because this particle that they talk about in the question has mass and charge. All right? So you'll have to account for the mass because the mass would give it weight. And if it's got weight, that's a force. So you're gonna have to think about a free body diagram. It's gonna take you, it kind of breaks it down into steps for you. Part A is find the angle, part B is find the next part, but you're gonna have to incorporate some things from first semester plus the little mini lesson from today to be able to pull that together. Now, I'm not gonna grade it as a, did you get it right or anything. It's just gonna, when we come to class on Friday, we're gonna have someone or a group of someones explain how you figured it out, and we'll talk it through. But that is something I'd like you to try. It is definitely a College Board level question because it incorporates things from multiple units. That's what they like to do. They don't generally give you questions in a vacuum of just one topic. They like to make you show that you can relate things across units. Okay? So that is your assignment. Any questions about that? Okay? Good luck with that. Good to see you guys all again. And we'll see you again on Friday.
Mine's kind of weird. Is that the one with the sphere hanging from the thread?
Yes.
Okay. Also, I have another question on this. So, this is gonna sound kind of weird.
Real quick and then,
I picked him up for the semis in
You're
Super Bowl.
yeah.
They have like an anvil